Question 1. Okay. This question is to find the relative molecular mass of an unknown liquid Y. A student used the following methods to determine the volume of conical flask. Okay, step 1. Okay, weigh a dry conical flask. Fill the conical flask completely with distilled water. Okay, weigh the conical flask with the distilled water again. Use the thermometer to measure the temperatures of the distilled water in the conical flask. Okay, so 4 simple steps. And after that, the student correct the results, and these are the results. We're going to use that for the calculations later. And okay, so for this figure 1.1, okay, show the variation of density of water with temperature. Okay, density versus temperature. Okay, later we will come back to this figure 1.1. Okay, let's see what it's asking. Use this figure 1.1 to determine the density of water at 23.0 degrees C. Give your answer in 4 decimal places. Okay, so at 23 degrees C, so you just from this figure 1.1, 23, then you will get about 0.9976, right? So from here, okay, so you just fill up here 0.9976. Okay, easy this one. Part 2, calculates the volume of the flask using the density of water determined in A1. Okay, density obtained now is 0.9976, less than 1. Now you need to first get the mass of water from the table right here. Use the second mass reading, right, minus the first mass reading, so you get the mass of water, right? Okay, so the mass of water at 23 degrees C is this one, 130.153. Okay, so the volume of water at 23 degrees C, so you need to use the gram of water over the density, because density is gram per cm cube. Eventually you get the cm cube. So you get a slightly larger value, 130.446. So you just put this volume into this part. Okay, part B. Another student determines the volume of a different conical flask to be 129.56 cm cube. Okay, this conical flask is used to determine the molar mass of the unknown volatile liquid Y. Okay, so these are the method. These are the steps that involve. First, cover the opening of the dry conical flask with aluminum foil. Secure using rubber band. Okay, something like this. Okay, put the aluminum foil on this conical flask. Then use the rubber band, secure the position. Right. Okay, and step 2. Weigh the conical flask, aluminum foil, and rubber band together. Record the mass. Okay, before the injection of the sample. Okay, step 3 is to inject the sample now. Use the syringe with a needle to make a small hole, right? Just make a small hole on this aluminum foil and inject about 5 cm cube of the liquid Y to the conical flask. Then remove the syringe. So therefore, this conical flask has a small holes. It's not really a closed system. Means some of the gases still can escape here, right? Because there is a small hole there. Now, step 4: place the conical flask in the water bath containing boiling water. Boiling water means temperature is 100 degrees C. Okay, boiling water. Allow all of Y to evaporate. So the volatile liquid Y might evaporate. So keep the conical flask containing vaporized Y in the boiling water for further 3 minutes. Okay, once it's vaporized, okay, we still need to put it further 3 minutes in the boiling water. Okay, make sure all form gas lah. Now, step 6. Carefully remove the conical flask from the boiling water and dry the outside surface thoroughly. Okay, so this is okay, second last step. Okay, last step. weigh the conical flask, aluminum foil, rubber band, and the contents, means the Y that form the vapor. Okay, records the mass. So now after these 7 steps, okay, part 1, suggest why the conical flask containing vaporized Y is kept in the boiling water for 3 minutes. So very easy. To ensure the vapor Y in the conical flask has reached the temperature of the boiling water, means in the simple way we say that is reach the thermal equilibrium with the boiling water. So means we need to make sure the this conical flask and together with the Y, the temperature is same as the boiling water. Then is when we calculate, then is more accurate. Okay, part 2, suggest why it is not necessary to determine the mass of the liquid Y injected through the conical flask by the syringe in the step 3. When it's still in liquid Y before it's formed gas, is not really needed to get the mass, because we're going to use the gas combined gas law, PV equal to nRT, is about either gas or gas. So when we use the mass of liquid, means it's not really accurate in that way. So it's not necessary. We need to make sure all the liquid Y form gas, then we can get the mass, then it's more accurate. Right? Okay, so the answer, this is from mark scheme. Right? The mass of the vapor that's occupying the flask will use in the molar mass calculation, means the combined gas law. So we just consider the mass of vapor, not the mass of the liquid. Part 3. The student thinks that Y is toxic. When you see toxic, means confirm is fume hood. So other than wearing the safety glasses or lab coat, state one safety precaution that must be taken. Carry out this experiment. Okay, whenever it's toxic compound, so it's better for us to use fume hood, because fume hood has a suction. It can suck out all the toxic gases, and it will not affect us then. Okay, part C. Table 1.2 shows the students' results. See, we have quite a numbers of results. Temperature of water bath. The pressure in kilopascal, 99. Okay, this is a mass of conical flask, aluminum foil, rubber band, measured in step 2. Okay, this is important. Mass of the conical flask, aluminum foil, rubber band, and Y measured in step 7. Also very important. We're going to use this one to get the mass of Y in the flask. So you use this one, okay, minus this, so you get this in the step 7. Okay, so this volume is already mentioned, right, in the step. Okay, though there is one part that you must be careful, because from this mass reading is 3 decimal places. 3 decimal places means the uncertainties, it will be 0.0005, because the minimum the value is actually 0.001. So half of this the graduation here, so is therefore 0.0005. Okay, so means each of the mass reading, the uncertainty, it will be 0.0005 for this part. And part 1, calculate the percentage error in the mass measured in the step 2. Step 2 is okay, let's go to this. Step 2 is the mass of the way the conical flask, aluminum foil, rubber band. So record the mass. Okay, many of you might thought that is one reading. So it's actually involved 2 readings. Okay, so why? Because many of us, when we get the mass reading, we will tear the and make sure it's 0 before we get the mass that we want. So after we tear the electronic balance, okay, and it show, let's say 0.000, after that, then we put the sample and measure again. So actually we read 2 times, means The 0 also considered as one reading. So that's why we need to use the uncertainties I told you just now. Okay, 0.0005 because it's a 3 decimal place balanced times 2. Okay, it's actually 2 balanced reading. So means before we put the let's say the sample, so we actually read the balance once, even though it's 0. So this considered as one time. And of course the other time is the actual mass reading. So that's why here is times 2. So just remember any mass reading, any mass reading for the solid sample or any sample that we measured, okay, most likely is involve 2 readings. Okay, so that's why we get this 2 times 0.0005 over this mass, right? This the step 2, 31.123 times 100%. So that's why you get this 3.21 times 10.83. Okay, part 2. The student assumes that the vapor formed from liquid Y is ideal gas, so that's why we can use the combined gas law. So PV equal to nRT. There is units for that. Pressure must be Pascal, volume must be meter cube, and all the gas constant you can get from the table, and the temperature must be in Kelvin. Okay, so for this part, okay, use the ideal gas equations. Calculates the amount in moles of Y in the conical flask in step 7. Assume the temperatures of the vapor form from the liquid is 100 degrees C. Follow the boiling water. Okay, so since PV equal to nRT, so means N equal to PV over RT. So make sure 99 kilopascal you convert to Pascal times 1000. Volume, then you need to change to the meter cube because the volume here is okay, this one cm cube. So you need to convert to the meter cube. Make sure it's meter cube, yeah. So means the volume in cm cube now need to times 10 power negative 6 convert to meter cube. So 8.31 is a gas constant. 100 degrees C convert to Kelvin. So plus 273. So eventually you can get this 4.138 times 10 power of negative 3 mole. Okay, part 3. Calculate the molar mass of Y. Okay, once you get the mole, then it's easy lah. So just remember the molar mass. Okay, it can be obtained when we have the mass together with mole. The mass is already given 0.306. Here 0.306. Then use the mole that calculated just now. You can get the molar mass. Okay, so use the mass over the mole, you get 73.95 gram per mole. Okay, so now this one is part D. This is a quite confusing one. I think many of you might not really know what is the meanings of this one in the mark scheme. The actual temperature of the vapor formed in the liquid Y is less than 100. Okay, so in the simple way, say that the actual temperature now is lower, is lesser than 100. Describe and explain the effects of this temperature on the calculated molar mass. Okay, this is the answer given in mark scheme. So what is the meaning? The calculated molar mass is greater than the true value. Okay, means it's larger. Okay, the reason is mass of the vapor measure is greater. So you need to link to this part. Okay, so imagine now these Y already formed vapor, and the actual temperature now is lower. Is telling us that the mass of the vapor remaining in the flask is more. Okay, higher temperature, then the mass of vapor is lesser because there is a hole there. So lower temperature means the vapor will remains there more, then means the mass is actually larger. That's the meaning. If it's higher temperature means the vapor might escape more, remain lesser, then mass is lesser. That's the meaning. So because N equal to PV over RT, N is mass over molar mass. Rearrange, you get the molar mass is equal to the MRT over PV. So if let's say lower temperature, the mass of the vapor is more, means because it remains, but more mass remains. So therefore, when the mass remains, means the mass is larger, then the molar mass also going to be larger. Okay, so that's the reason why, you see, that's the reason. It's greater than the true value, the calculated one. It's only because the mass of the vapor is greater. Okay, part E. The boiling of the methyl benzene is 111 degrees C. Suggests why molar mass of the methyl benzene cannot be determined using this method. It's quite easy because boiling water is 100 degrees C only. Since the boiling point of methyl benzene is much higher than this, so means it will still remains as the liquid most likely. It will not really fully form gas or vapor. That's the reason. Temperature of the water bath not high enough to boil this methyl benzene. Okay, that's all. Thank you.